Welcome! In this session, we'll be exploring LeetCode problem number 333, largest BST subtree. This is a fascinating problem that challenges our understanding of binary trees and binary search trees. We'll walk through the process of identifying the largest subtree within a binary tree that satisfies the properties of a BST. Let's dive in. In this problem, you're given the root of a binary tree, and the goal is to determine the size of the largest subtree that qualifies as a binary search tree, or BST. To clarify, a binary search tree is a special kind of binary tree where every node follows specific rules. The left subtree of any node must only contain nodes with values less than the node's value, while the right subtree must only contain nodes with values greater than the node's value. Additionally, for a tree to be considered a BST, both its left and right subtrees must also independently satisfy these BST properties. A subtree, in this context, is any part of the tree that starts at a particular node and includes all of its descendants. The input to the problem is the root node of the tree, which contains a value, and pointers to its left and right children, if they exist. The output we need to produce is an integer representing the size of the largest subtree that meets the binary search tree criteria. Let's look at some examples to better understand the problem. In the first example, we have a binary tree where the root node is 10, with two child nodes, 5 on the left and 15 on the right. The left child, 5, has two children of its own, 1 on the left and 8 on the right. On the right side of the root, the node 15 has a single child, 7, on its right. In this case, the largest BST subtree is the one rooted at the node with value 5. This subtree includes the nodes 5, 1, and 8. It satisfies the BST properties because 1 is less than 5, 8 is greater than 5, and both the left and right subtrees of 5 are valid BSTs. The size of this subtree is 3, so the output for this example is 3. Now, let's analyze why the subtree rooted at 10, which is the entire tree, is not a BST. While most nodes in the tree follow the BST rules, the node 7 violates the property. Since 7 is in the right subtree of 10, its value should be greater than 10, but it isn't. This disqualifies the entire tree from being a BST. Moving to the next example, we have a tree with root node 4, left child 2, and right child 6. The node 2 has children 1 and 3, while the node 6 has a single right child, 8. Here, the entire tree satisfies the BST properties. Each node's left child is smaller, and its right child is larger, making the entire tree a valid BST. The size of this tree is 6, so the output is 6. Finally, consider the case where the root node is 1, with two child nodes, 2 on the left and 3 on the right. Neither the left subtree, rooted at 2, nor the right subtree, rooted at 3, satisfies the BST properties. The left child, 2, is greater than the root, which breaks the rule that all nodes in the left subtree must be smaller than the root. Similarly, the right child, 3, is greater than the root, but it doesn't have any valid BST descendants. In this scenario, the largest BST subtree consists of just one individual node, since no larger subtrees qualify as BSTs. The output is therefore 1. When solving this problem, we must also consider edge cases, such as an empty tree, which should return 0, or a tree with only one node, which is always a valid BST and has a size of 1. Performance considerations are also important, especially for deep or unbalanced trees, as the number of nodes can go up to 10,000. To solve the problem of finding the largest BST subtree, we began by considering a brute force approach. The intuition here is straightforward. For each node in the tree, we treat its subtree as a potential BST and validate whether it satisfies the properties of a binary search tree. If it does, we calculate its size and track the maximum size across all nodes. The process involves a recursive traversal of the entire tree, where for each node, we validate the BST properties, ensuring that all nodes in the left subtree are smaller than the current node and all nodes in the right subtree are larger. While this method is conceptually simple, it requires validating each subtree independently, which involves repeated work. For example, the same subtree might be validated multiple times during recursive calls. As a result, the time complexity becomes n squared, in the worst case, making this approach impractical for large trees. This inefficiency is the primary drawback of the brute force method, particularly when working with trees containing many nodes. To address the inefficiency of the brute force approach, we turn to an optimized strategy that uses post-order traversal. This method processes nodes in a bottom-up manner, ensuring that information about the left and right subtrees is available before evaluating the current node. At each step, we gather critical details about the left and right subtrees, including whether they are valid BSTs, their minimum and maximum values, and the size of their largest BST subtree. Using this information, we can determine if the current node forms a valid BST with its subtrees. Specifically, the current node's value must be greater than the maximum value of the left subtree and smaller than the minimum value of the right subtree. If these conditions are met, we calculate the size of the BST rooted at the current node by summing the sizes of the left and right subtrees and adding 1 for the current node. If the conditions are not met, we propagate the size of the largest BST found in one of the subtrees. This approach eliminates redundant validations and processes each node only once, resulting in an efficient O(n) time complexity. By leveraging the results of child nodes, we avoid repeated work and achieve a significant performance improvement over the brute force method. Given the trade-offs between simplicity and efficiency, the optimized approach using post-order traversal was chosen as the preferred strategy. This method not only ensures correctness but also achieves optimal performance. The key insight here is that we can validate BST properties and compute the size of the largest BST subtree simultaneously during a single traversal. Post-order traversal is particularly well suited for this task because it processes child nodes before the parent node, ensuring that all necessary information is available when evaluating the current node. This eliminates the need for redundant checks and makes the approach scalable to large trees. While the brute force method is easier to implement, its O(n)² complexity limits its practicality to smaller inputs. The optimized approach, on the other hand, is slightly more complex but operates in linear time, making it much more efficient for handling larger trees. By leveraging dynamic programming principles during traversal, we achieve a solution that balances elegance and efficiency. The critical breakthrough in this problem was recognizing that BST validation and size computation could be integrated into a single traversal using postorder. This insight allowed us to propagate essential information, such as minimum and maximum values, subtree sizes, and validity, from the child nodes to their parent. By doing so, we ensure that each node is processed only once, achieving optimal efficiency without compromising correctness. The optimized approach was selected because it strikes the right balance between clarity and scalability. It avoids the inefficiencies of brute force while maintaining a clean recursive structure that is both intuitive and aligned with the constraints of the problem. This method not only handles large inputs gracefully but also provides a systematic way to solve the problem by reusing results from child nodes. The ability to validate BST properties and compute sizes simultaneously during traversal is what makes this approach particularly powerful and elegant. To solve the problem of finding the size of the largest binary search tree, or BST, subtree within a given binary tree, we adopt a postorder traversal approach. This means we process the child nodes of a subtree before the parent node itself. The algorithm begins by defining a helper function, DFS, node, which is recursive and computes key information for each subtree rooted at a specific node. The function returns a tuple containing 4 elements, whether the subtree is a valid BST, the size of the largest BST within the subtree, and the minimum and maximum values in the subtree. These details are critical for validating the BST property as we traverse up the tree. For the base case, when a node is none, we consider the subtree to be an empty BST, returning a size of 0 along with extreme values for comparison purposes. This simplifies the validation logic for the rest of the tree. Now, we make recursive calls within the helper function to process the left and right children of the current node. From these calls, we obtain detailed information about the left and right subtrees, such as whether they are BSTs, their sizes, and their minimum and maximum values. Using this information, we can determine whether the subtree rooted at the current node satisfies the BST property. Specifically, the current node must have a value greater than the maximum value in the left subtree and less than the minimum value in the right subtree, with both subtrees themselves being valid BSTs. If these conditions are met, the subtree is a BST, and we calculate its size as 1 for the current node, plus the sizes of the left and right subtrees. We also update the minimum and maximum values to reflect the entire subtree. If the subtree is not a BST, we return the size of the largest BST found in either the left or right subtree, discarding the current node's contribution. Additionally, we we keep track of the largest BST size encountered during the entire traversal. This ensures that we can return the correct result after processing all nodes in the tree. When implementing the algorithm, we must consider several edge cases. For example, if the input tree is empty, the largest BST size is 0. If the tree contains only one node, it is inherently a BST of size 1. Similarly, if the entire tree satisfies the BST property, the global maximum size will equal the number of nodes in the tree. Cases where only certain subtrees violate the BST property are handled seamlessly by the algorithm's recursive structure. This approach leverages post-order traversal to evaluate each subtree only after processing its children. By passing the minimum and maximum values up the recursion stack, we avoid redundant computations and ensure efficient validation. The divide-and-conquer nature of this problem allows us to break it down into smaller subproblems, combining their results to solve the larger problem. This algorithm achieves a time complexity of O(n), where n is the number of nodes in the tree, as each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursion stack. These efficiencies make the approach well-suited for large trees. In terms of data structures, the recursive stack facilitates post-order traversal, while tuples returned by the helper function summarize critical information about each subtree. To understand the algorithm in practice, let's consider a specific example. Imagine a binary tree with the root node 10, and its left and right subtrees rooted at 5 and 15, respectively. The left subtree of 5 has children 1 and 8, while the right subtree of 15 has children 12 and 20. Using this structure, we will process the tree recursively to identify the largest BST. Starting at the root node 10, we analyze its left and right subtrees. For the subtree rooted at 5, the left child 1 and the right child 8 are both valid BSTs. Since the value 5 lies between these child values, the entire subtree rooted at 5 is a BST of size 3. Similarly, for the right subtree rooted at 15, both child nodes 12 and 20 form valid BSTs, and the value 15 maintains BST validity. Thus, this subtree is also a BST of size 3. Finally, at the root node 10, we verify that its value lies between the maximum value of the left subtree, 8, and the minimum value of the right subtree, 12. This makes the entire tree a valid BST with a total size of 7. Therefore, the size of the largest BST subtree is 7, which is the entire tree in this case. This implementation solves the problem of finding the largest BST subtree in a binary tree using a recursive post-order traversal approach. The helper function DFS traverses the tree and evaluates each subtree to check whether it satisfies the properties of a BST. Explanation. 1. Base case. If the current node is none, we return true, 0, INF, to indicate that an empty tree is a valid BST with size 0 and extreme boundaries for min and max values. 2. Recursive calls. DFS, node.left, and DFS, node.right, recursively evaluate the left and right subtrees and return information about whether these subtrees are BSTs, their sizes, and their minimum and maximum values. 3. BST validation. A subtree rooted at node is a BST if both left and right subtrees are valid BSTs. The maximum value in the left subtree, left_max, is less than the current node's value. The minimum value in the right subtree, right_min, is greater than the current node's value. 4. Update results. If the current subtree is a BST, calculate its size as left_size plus right_size plus 1. Update the minimum and maximum values for the subtree. 5. Handle non-BST cases. If the subtree is not a BST, propagate the maximum size found so far from either the left or right subtree. 6. Final result. The DFS function computes the size of the largest BST subtree as part of its return values. The largest BST subtree function simply extracts this size and returns it. This approach ensures that we traverse each node exactly once, making the time complexity O(n), where n is the number of nodes in the tree. The space complexity is O(h), where h is the height of the tree, due to the recursion stack. Here, we begin the Java implementation for the largest BST subtree problem. The solution is built around a helper function called DFS, which performs a depth-first search to analyze each subtree. The main method, largest BST subtree, simply calls this helper function on the root node and extracts the size of the largest BST subtree from the result. Now, within the DFS method, we start with the base case. If the current node is null, we return an array indicating that this subtree is a valid BST of size 0. The array structure is BST size, min, max, where BST is a flag denoting whether the subtree is a valid BST, size is the number of nodes in the subtree, and min and max represent the range of values in the subtree. For null nodes, we use integer.max_value and integer.min_value to initialize the range. Next, we recursively process the left and right subtrees, collecting their results in the left and right arrays. After that, we check whether the current node and its subtrees together form a valid BST. This is done by verifying that both the left and right subtrees are valid BSTs, and the current node's value lies within the correct range, greater than the maximum value in the left subtree and smaller than the minimum value in the right subtree. If these conditions are satisfied, we calculate the size of this BST by summing the sizes of the left and right subtrees and adding 1 for the current node. We also determine the new minimum and maximum values for the subtree to update the range. Finally, we return an array indicating that this subtree is valid, along with its size and range. If the subtree rooted at the current node does not satisfy the conditions for being a valid BST, we simply propagate the largest size found so far. This ensures that even if the current subtree is invalid, we still capture the size of the largest valid BST in its subtrees. Now, moving on to the tree node class, this is a standard definition for a binary tree node. Each node contains an integer value, along with pointers to its left and right children. The class includes two constructors, one for creating a node with a value and no children, and another for creating a node with both a value and specified left and right children. This completes the implementation. The overall approach leverages the depth-first traversal to efficiently compute the largest BST subtree size in n time, ensuring that each node is visited only once. To begin, we are working with a simple binary search tree where the root node has a value of 2, and its left and right children have values 1 and 3, respectively. First, the largest BST subtree function is called with the root node, and the helper function DFS initiates a recursive traversal. Starting at node 2, we move to its left child, node 1. At node 1, we explore its left and right children, which are both null. Since an empty subtree is always a valid BST with size 0, these calls return true, 0, INF. Now, at node 1, we check if the subtree rooted here satisfies BST conditions. Both its left and right subtrees are valid BSTs, and the condition left_max1 right_min holds true, so the subtree is confirmed as a BST of size 1, with minimum and maximum values both being 1. Next, we return to node 2 and move to its right child, node 3. At node 3, both children are also null, so the DFS calls return true, 0, INF for each child. The BST conditions for node 3 are satisfied, making it a valid BST of size 1, with both minimum and maximum values as 3. Now, back at the root node, we combine the results from the left and right subtrees. The left subtree rooted at node 1 is a BST of size 1, and the right subtree rooted at node 3 is also a BST of size 1. Additionally, the condition left_max2 right_min holds true for the values 1, 2, and 3. This confirms that the entire tree is a valid BST. The size of this BST is the sum of the sizes of the left and right subtrees plus 1 for the root node, giving us a total of 3. This is the largest BST subtree in this example, and the function returns 3 as the result. Moving on to the second example, we now have a tree with root node 10, a left child 5, and a right child 15. Below node 5, there are children 1 and 8, while node 15 has a right child 7. We begin the traversal at node 10 by first exploring its left subtree rooted at node 5. At node 5, we start with its left child, node 1. Since node 1 has no children, the DFS calls return true, 1, 1, 1 for this subtree. Next, we move to node 5's right child, node 8, which also has no children. Similarly, DFS returns true, 1, 8, 8 for this subtree. At node 5, we now evaluate its subtrees. The left subtree rooted at node 1 is a valid BST of size 1, and the right subtree rooted at node 8 is also a valid BST of size 1. Additionally, the condition left underscore max 5 right underscore min holds true for the values 1, 5, and 8. This confirms that the subtree rooted at node 5 is a valid BST, with a total size of 3. The minimum value in this subtree is 1, and the maximum value is 8. Returning to the root node 10, we now explore its right subtree rooted at node 15. At node 15, we first check its left child, which is null, so DFS returns true, 0, INF. Next, we move to its right child, node 7. Since node 7 has no children, DFS returns true, 1, 7, 7 for this subtree. Now at node 15, we evaluate its subtrees. The right subtree rooted at node 7 is a valid BST of size 1, but the BST condition left underscore max less than 15 right underscore min fails because 7 is not greater than 15. This means the subtree rooted at node 15 is not a valid BST, and we return false, 1, 0, 0. Back at the root node 10, the left subtree is a BST of size 3, but the right subtree is not a BST. Therefore, the largest BST subtree in this example is the one rooted at node 5, with size 3. Finally, let's look at the third example, where all nodes have the same value of 2. The root node has 2 children, both also valued 2. We start at the root and first evaluate its left child. At this left child, we explore its null children, which both return true, 0, INF. However, when we check the BST condition left underscore max 2 right underscore min, it fails because duplicate values are not allowed in a BST. As a result, the subtree rooted at this node is not a valid BST, and DFS returns false, 0, 0, 0. Similarly, for the right child of the root, the same process occurs, and the subtree is also deemed not a BST with a return value of false, 0, 0, 0. At the root node, since neither the left nor the right subtrees are valid BSTs, the entire tree is not a BST. The largest BST subtree in this case has a size of 0, and the function returns 0 as the result. The time complexity of our solution is O, n, where n represents the total number of nodes in the binary tree. This efficiency comes from the fact that the algorithm traverses each node exactly once using a recursive depth-first search, or DFS. Within each recursive call, we perform constant-time operations, such as comparing values and updating variables like the size or the minimum and maximum values within the subtree. These operations have a time complexity of O(1) per node. Since the recursive function is invoked for every node in the tree, and each invocation takes constant time, the overall time complexity scales linearly with the number of nodes, leading to O(n) as the final time complexity. The space complexity of our solution depends on the height of the binary tree, which determines the maximum depth of the recursive call stack. This is because recursion requires additional memory for each function call. In the worst-case scenario, such as a skewed tree, the height of the tree could be O(n), meaning the space required for the call stack would also grow to O(n). However, in the best case, where the tree is perfectly balanced, the height is only O log n, resulting in a significantly smaller stack size. Additionally, the algorithm does not use any extra data structures, relying instead on in-place calculations with a fixed amount of auxiliary variables like left_is_bst and left_size. This contributes only O(1) auxiliary space. Therefore, the overall space complexity is determined by the recursion depth, which we denote as OH. When analyzing the best, average, and worst cases, we start with the best-case scenario, which occurs with a perfectly balanced binary tree. In this case, the height of the tree is O log n, and since we still visit every node, the time complexity remains O(n), while the space complexity is O log n, due to the recursion stack. For the average case, a typical binary tree also has a height around O log n, leading to the same time and space complexities as in the best case, O(n) for time and O log n for space. However, in the worst case, where the binary tree is completely skewed, the height becomes O(n). As a result, both the time complexity and the space complexity reach O(n), with the call stack growing proportionally to the height of the tree. When comparing the optimized solution to a naive or brute force approach, the efficiency gains become clear. A naive solution might involve validating the BST property for every possible subtree, which requires O(n) time for each node. With n nodes in the tree, this would result in a total time complexity of O, n squared. The space complexity for a naive method would still be O, h, due to the recursion depth. In contrast, the optimized solution uses a post-order traversal to compute the BST properties and subtree sizes in a single pass. By doing so, it reduces the time complexity to O, n, while maintaining the space complexity at O, h. This approach is far more efficient, especially for larger trees. To mathematically justify the big O complexities, consider that the binary tree has n nodes. Each node is visited exactly once during the traversal, and the operations performed on each node, such as comparisons and arithmetic, take constant time O1. Multiplying O1 by n nodes gives a total time complexity of O(n). For space, the recursion depth is limited by the tree's height, h. In a balanced tree, h is O log n, while in a skewed tree, h is O(n). Thus, the space complexity is O(h). In conclusion, this solution is both time and space optimal, especially when compared to brute force methods, making it an efficient choice for this problem. When solving the largest BST subtree problem, there are several common mistakes to watch out for. First, not handling edge cases properly can lead to runtime errors. For example, if the tree is empty or consists of just one node, your solution must account for these situations explicitly. Next, incorrect BST validation is another frequent issue. Many people mistakenly check only the immediate children of a node, but to validate a BST, you need to ensure that all nodes in the left subtree are less than the root, and all nodes in the right subtree are greater than the root. Another pitfall is performing redundant traversals. If you calculate properties like size and validity in separate passes, it can make your solution inefficient. Strive for a single traversal that handles both. Lastly, some misunderstand the problem itself, thinking it's just about finding the largest subtree by node count, rather than ensuring the subtree is a valid BST. Be sure to clarify the requirements before diving into the implementation. Now, let's talk about a few more considerations and insights. Ignoring integer overflow and range checks can be a subtle but critical issue, especially in languages like C++ or Java. While using float, INF, and float, INF, for ranges works in many cases, you should be cautious when dealing with edge cases involving very large values. If you're implementing custom range handling, make sure to account for the possibility of overflow. On the interview side, this problem is an excellent opportunity to demonstrate your understanding of recursive patterns. Structuring your recursion to return multiple values, such as whether the subtree is a BST, its size, and the minimum and maximum values, can make your solution both elegant and efficient. Speaking of efficiency, aim for an O(n) solution that combines BST validation and size computation into a single traversal. This approach not only optimizes performance but also shows your ability to write well-thought-out code. Finally, during an interview, it's important to clearly explain your intuition. For example, articulate why you're combining multiple checks into one traversal and how this reduces redundancy. This demonstrates both your problem-solving skills and your understanding of trade-offs. Additionally, mastering range-based validation is a valuable skill, as it's a common requirement in many tree-related problems. If you practice this technique, you'll find it much easier to solve similar challenges in the future. Speaking of related problems, several LeetCode questions tie closely to this one. LeetCode 98, Validate Binary Search Tree, is a foundational problem that focuses on BST validation. LeetCode 110, Balanced Binary Tree, combines validation with height computation, making it another important problem to practice. For a more advanced variation, LeetCode 1373, Maximum Sum BST in Binary Tree, requires you to calculate the maximum sum of all BST subtrees. Finally, LeetCode 250, Count Univalue Subtrees, is another interesting challenge where you count subtrees that meet specific conditions, which is very similar in structure to this problem. Working through these related problems will strengthen your understanding of binary tree algorithms and prepare you for a wide variety of scenarios. Finally, let's discuss some alternative approaches and their trade-offs. A brute force approach involves checking every node to determine if its subtree is a valid BST and calculating its size. While this is straightforward to implement, it's highly inefficient, with a worst-case time complexity of O(n) squared due to redundant traversals. On the other hand, the optimized recursive approach uses bottom-up recursion to validate the BST and compute its size in a single traversal. By returning multiple values, like whether the subtree is a BST, its size, and its min and max values, you can achieve an O(n) solution. This method is slightly more complex to implement but is incredibly efficient and well-suited for interviews. Another option is the divide and conquer strategy, which involves solving the problem for the left and right subtrees and then combining the results. While this can also achieve O(n) complexity when done carefully, redundant checks may arise without meticulous implementation. Each method has its merits, but the optimized recursive approach is generally preferred for its balance of efficiency and clarity. Great job! Today, we tackled the largest BST subtree problem and explored an efficient solution using post-order traversal. Remember, mastering tree problems requires practice and a deep understanding of traversal techniques. Thanks for tuning in, and don't forget to subscribe for more problem-solving sessions. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!